Hi, welcome back to Unit 8, topic 8.4. This is going to be fluids and conservation laws. So again, we've been talking about how fluids are affected by the concepts that we've already discussed. In the last video, we talked about in terms of Newton's laws. Now let's talk about in terms of the conservation laws. Okay, mostly conservation of energy and conservation of mass. All right, so a difference in pressure is what's going to cause the actual fluid to begin to flow. So everything that we've talked about before now, the fluid is really just like shifting around. It's not moving, but it's just kind of shifting around from place to place. Here we're going to talk about what happens when the fluid begins to move, okay? And what we want to look at is something called the volume flow rate, all right? And so there's two things that we look at. So the rate at which matter enters a fluid-filled tube, open at both ends, must equal the rate at which the matter exits the tube. And then the rate at which matter flows into a location is proportional to the cross-sectional area of the flow and the speed at which the fluid flows. So this is something called volume flow rate. So there's two equations for this, right? So basically the first one is Q equals V over T, where V is volume and T is time. And you can think about it as like dV dt, okay? Or delta V over delta T. And so this is how much volume flows through in a particular moment in time. Now, what we just talked about is another equation for Q, and it's simply A times V, okay? A times V, that tells us it's the cross-sectional area times the speed at which it is flowing through. So if I have a pipe, right, and I want to take, how much is flowing through at this point in time, I'm going to have a cross-sectional area of the pipe, right? That's going to be our A. And the fluid's going to be flowing through here with a speed of V. That's how much volume, or that's how much fluid is flowing, or how fast the fluid is flowing. Okay, so you can just also say that AV equals, not Q, because we know that's what it is, but AV equals V, capital V divided by T. And you can do some manipulation of this equation to figure out, like, what is the volume, how long does it take? But the main thing that we're going to talk about, or what we want to talk about, is the continuity equation. So the continuity equation for fluid flow describes conservation of mass. So here's our first conservation law that we encounter. So it's the fluid flow describes, the continuity equation for fluid flow describes conservation of mass flow rate in an incompressible fluid. So basically what that's saying is, like, anywhere in the fluid, the amount of volume flowing through that fluid, right, or through that pipe, is just going to be equal to each other. Okay, and so if we substitute in, essentially this is the continuity equation you'll see in textbooks. A1 V1 equals A2 V2. So what does that mean if we have a pipe that looks like this? Okay, so these have two different cross-sectional areas. But what's going to happen is the same flow rate is going to go through both of them, but what you're going to see is, in the larger section, you're going to have a low V because you have a big area. And in the smaller section, you're going to have a large V because you have a small area. Okay? In the upper right-hand corner, you see a real-world example. Taking a hose and putting your thumb over the top. So what you're doing is it's going to have a cross-sectional area of the hose until you put your thumb over the top, and then it's going to have a smaller area through which it's going to try to travel through, creating a faster stream. Okay, so this all leads us talking into, the next conservation law. So we have a difference in gravitational potential energy between two locations in the fluid result in a difference in kinetic energy and pressure between those two locations that is described by conservation laws. So Bernoulli's equation describes the conservation of mechanical energy in fluid flow. Okay, so here's our second conservation law, right? Conservation of mechanical energy. And so what we say is some sort of reference pressure plus 1/2 rho V0 squared plus rho G H0, that is going to equal a constant, right? So what happens is when you break it down, this is our kinetic energy component, and this is our potential energy component. So what does that mean? If I have a pipe that looks like this, right, a height difference, right, is going to cause, pressure to change. If it's flowing through, right, which is going to cause speed differences and so forth. But what happens is when you have larger areas, the pressure is going to be higher. And when you have smaller areas, the pressure is going to be lower. Now, how is this important? You have wings, right, which you see here in the middle, to the right in the middle. That's what's creating this lift force, okay? So what happens is as air encounters the front of the wing, right, it's going to split. And because you have a larger surface area on top for it to flow over, you're going to create less pressure, right? Because it's going to be faster than on the bottom, right? So here you're going to have a smaller V. Here you're going to have a larger V, which means pressure on the bottom is going to be up, pressure on the top is going to be down. And because of this pressure difference, you're going to get a net upward force that we know as lift. Spoilers on cars are the opposite of this. So if you take your head and you turn your head over, right, you'll find how does a spoiler on a car work. So the top part is the shorter distance for the air to travel, and the bottom part is the longer. So you create the opposite effect. And then the last thing here that we're going to talk about is something called Torricelli's theorem. There should be, or I will have a YouTube short centered around this. I actually have a 3D printed a Torricelli's demonstration device. So it relates the speed of a fluid exiting an opening to the difference in height between the opening and the top surface of a fluid, and we derive from the conservation of energy principles. So what does that mean? The faster an object goes, the lower it is in the, sorry, I'm looking up. So the lower a hole is, right, the faster it's going to be, because it's going to have a stronger jet. It's going to have more volume or more fluid pressing down on it, causing it to go out faster. And you can see here in the diagram, so at the top, you're going to have the weakest jet, and at the bottom, you're going to have the strongest jet. Sorry, there's a bullet point there. I don't know if there's an equation. Oh, we do. So V equals the square root of 2G delta Y. That should look very familiar because that is the speed using conservation of energy. Okay. Now, if you're watching this in 24-25 school year, this is the first year with fluids in the curriculum. I'd almost guess that there may be a question relating to Torricelli's theorem or this concept to projectile motion, which is very common because you can find the speed of it, how fast it's coming out of a hole in a container, and then you can calculate where it lands, because then it just becomes, that fluid becomes a projectile. Okay, so let's look at an example problem. All right, so here we have the classic thumb over the nozzle, right? So you have a nozzle with a radius of 0.250 centimeters attached to a garden hose with a radius of 0.90 centimeters. The flow rate through the hose and nozzle is 0.50 liters per second. So this is our Q, but we need this in cubic meters per second. So that's, again, remember 1 liter is 1.0 times 10 to the negative 3 cubic meters. So that just makes this 0.5 times 10 to the negative 3 cubic meters per second. Okay. We're going to calculate the speed of the water in the hose and then in the nozzle. And then we're going to calculate the pressure in the hose, given that the absolute pressure in the nozzle is atmospheric pressure. Okay. So first question, we're going to do Q equals AV for both scenarios, right? And A, because it is a hose, is pi r squared. So for each one, we're going to do pi r squared times V. Okay. And what we want to do is we want to solve this for V, so you get Q over pi r squared, or Q over area. So for the nozzle, you have 0.5 times 10 to the negative 3 divided by pi times, and we want the nozzle, 0.25 times 10 to the negative 3 squared, or sorry, negative 2 squared. Okay, and so coming out the nozzle, you'll see it's going to go 25.5 meters per second. And that follows as expected because we know with the smaller area, we should have the faster speed. All right, and then if we talk about the hose, the volume flow rate will not change. Oh, sorry, we have pi times now our radius is 0.9. And you're going to see this is going to be much slower. It's about 2. Sorry, I'm just trying to get through this for some reason. All right, so the velocity coming out of the hose is going to be 1.96 meters per second. So you can see that, nozzle versus hose, the difference in the speed. It's almost a 10 times, it's 10 times bigger in the nozzle than it is in the hose. All right, so there's your A and B. Now for part C, we're going to calculate the pressure in the hose. So what we need to do is use Bernoulli's equation. One. So we're going to essentially treat it as a conservation or energy question. Okay, so we write down Bernoulli's equation, and we kind of let's see if we can cancel anything out. We know there's not going to be a difference in the height. Now there's going to be a slight difference because you're going to go from 0.9 to 0.25. That's not a significant difference in terms of the height difference. Okay, so we have P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Now here you're just going to call one, hose 1, nozzle 2, or nozzle 1, hose 2. So it doesn't matter. The only thing you have to remember is whichever one the nozzle is, you have the pressure, right? And you're going to solve for the other pressure. So P1 is going to equal P2 plus 1/2 rho, because it's going to be the same fluid, V2 squared minus V1 squared. So this is telling me that 2 is going to be the nozzle and 1 is going to be the hose. And so we're solving for the hose. So we have 1.01 times 10 to the 5, plus 1/2 the density of water, which is 1,000. And then we do 25.5 squared minus 1.96 squared. Okay. And then it tells us that we're going to have a pressure of 4.24 times 10 to the 5th pascals, or newtons per square meter. So as you can see with the larger part, right, because we're looking at the hose, you're going to have a greater pressure. Okay, so there it is. This is AP Physics 1. This was Unit 8. Now it's time to prepare for that exam.